So my name is Danno Ferrin. I have been an Ethereum core developer since about 2013. Not 2013, 2018. I've been in blockchain since 2013. But I am currently working at Swirlds Labs as a principal software engineer, integrating some of their EVM work into it. But what I'm here to talk about today is about Ethereum, about where it came from and where it's going. And so these are the three topics we're going to talk about in our deep dive. I'm going to do where Ethereum's been and where it's going. The protocol fellowship will be talked about by Josh. And Pooja will have the process of protocol governance. But when I look at Ethereum, it's done a lot of interesting things and gone a lot of interesting places. And it's going to be going some even crazier places. So it's kind of like wandering around and doing all sorts of interesting things. But to get our bearings, I think first we need to start with where Ethereum's been. And one of the things that's established Ethereum is its pattern of using hard forks to change the rules of its network. It's been doing this since 2015. 2016 was its first hard fork. So here's a quick timeline showing the past nearly 10 years, coming up on 8 years, but 7 of the past 8 years. And if you look at the top, this lists the hard forks that were occurring in something called the execution client. And those are going on pretty typically until about the end of 2020. And then something started developing on the bottom called the consensus layer. And those two layers kind of merged together here back in September of last year. A really interesting thing has happened is that from the beginning of Ethereum, they always wanted to be a proof of stake blockchain, but the technology wasn't there at first. All they had was proof of work. So they started with proof of work, and then when things were ready, they changed over there. But along the ways to becoming a proof of stake blockchain, a lot of interesting things happened. So I'm going to highlight 4 of the things that happened in the past that kind of set how Ethereum is set up for in the future. Probably the first thing is probably the worst thing that ever happened to Ethereum, and that was the DAO fork. There was a smart contract called the DAO that at one point had locked up 1 out of every 7 Ethereum in all of Ethereum at that point. And someone found a way to steal money out of it. So this was an early existential crisis, and they did something that they only did once. They did something called an irregular state change, where they decided that the stolen money no longer existed, and that the money that was locked, people could get to. This permanently forked Ethereum. Some people really didn't like it, and they went and formed a different blockchain called Ethereum Classic. These two chains still exist to this day, Ethereum Mainnet and Ethereum Classic. They forked from this experience. The next thing that happened at the next DevCon in Shanghai, something called the Shanghai attacks. A very smart person, we don't know who it is, figured out how to exploit the performance characteristics of one of the main Ethereum clients at the time, Geth. It wasn't as optimized as it is today. There were some issues with some of the storage, not aligned with how much it costs in the gas schedule. This is a success of the multi-client architecture of Ethereum, because parity Ethereum was able to keep the network running while we figured out the problems. And we changed some of the gas schedule things to fix some of the nature of the problem with the attack. A couple of years later, there was a fork that was supposed to be called Constantinople, and we were still tinkering with the gas schedule. Except someone, 2 days before we were supposed to fork mainnet, figured out that this tinkering of the gas schedule was going to break contracts that were out there. And that is something that after the DAO hack, that we were committed to not do again if we can avoid it. So on 30 hours notice, we canceled the fork. We got all the node operators together, got all the mining pools together we could, shouted as loud and as far as we could get, and on 30 hours notice, we were able to delay the fork. We redid it minus the gas changes in something called Petersburg a few months later. And eventually it came back in a corrected fixed version, came back in a different version in another fork about a year later. And the last thing that I think is important to notice about all of these is about half of those forks that were listed up there are altering something called the difficulty bomb. Going with Ethereum's early commitment to transition to proof of stake, they put in something that was going to make proof of work ultimately impossible unless there was a transition to the consensus algorithm. It took a lot longer than estimated. They thought it'd take about 2 years. It took about 7. So at 6 different times, 3 as part of normal forks, and 3 forks that did nothing more than delay this bomb, they delayed the time that the bomb would explode and stop the network from running. This last one, Great Glacier, needed to push it back 2 months to give the 2 final months that was needed for the Ethereum merge to happen. So in summary for these forks, what you can learn from these is most of these changes were what I would term reactionary. There were requests from developers saying, hey, we need this feature, we need block caches, we need shift operations, or there were changes to the gas schedule to make things more or less expensive to match the real execution costs within the clients. Sometimes there are attack mitigations, dealing with various changes. There are only, I would say, 2 changes in all these forks that were really forward-looking. The one that most deserves the title of the forward-looking change would be EIP 1559, which spawned the entire ultrasound money main. So whenever there's a transaction, a certain amount of that transaction is always burned, and the user experience is great in that you're only charged what the network is actually charging for your transaction at the time. It's a forward-looking change that when you combine it with the merge, Ethereum is now net deflationary. No one needed that, we wanted it, so we did it. The other one that's forward-looking, hasn't fully executed yet, is a prefix on EVM bytecode to preserve space for the Ethereum object format, for the EVM object format. So that was a bit of a brief history. Now let's talk about current history. The most important thing that happened in Ethereum's history happened last September, and it finished about 2 weeks ago. And that, of course, was the merge. So this is a bit of a schematic that Ethereum Foundation used to show what was going on with Ethereum. At the beginning of time, we had a proof of work network, and the red box represents the proof of work consensus driving the state that is the black line. About December of 2021, or 2020, it's been a while ago, I can't remember exactly when, but the beacon chain launched. And the beacon chain, what it did is everyone put all of their ether into a contract that had no way out, and the only way out was to be activated through the beacon chain and merged. It was a big leap of faith for a lot of the people believing in the merge, but a lot of them believed in it, so they locked up their ETH, and they launched the beacon chain. And for about 2 years, this chain ran parallel to the proof of work chain, and all it did was it kept consensus of who's donated, who's committed stake, and who hasn't. So finally, in last year, in the 3rd quarter, we merged. And there was so much work that had gone in to do all this work, so much planning and practicing, that basically nobody on the network noticed that a merge happened. You need to be very well instrumented to figure out that things actually changed. That's how smooth the merge went. And it's a great testament to all the effort put on by the core developers at Ethereum Foundation to make sure that that went seamlessly. However, there was one piece of thing that they didn't quite get in time, that they prioritized the merge over a step called withdrawals. And that's what activated 2 weeks ago in the Shanghai fork. Now that you can merge, you can unmerge, you can take your money, not merge, now you can stake, and then you can take your Ethereum that has been staked, and you can move it back out into your own account. So we have full life cycle staking now available in Ethereum. And this is quite amazing. We used to have one of the second largest proof of work blockchain, and now Ethereum is the largest proof of stake blockchain by a number of measures. So let's dive into some of the details of what the merge looks like. On the left here, you see a representation of a typical Ethereum block pre-merge. You got a list of transactions, you got the difficulty, you got a bunch of administrative data pointing to the previous block, what time it thinks this block is. And surrounded around it is the consensus mechanism, the proof of work mechanism that was driving these blocks forward. The clients would make the blocks, and proof of work would seal the blocks and commit them to the blockchain. Post-merge, it looks a little different, but not too different if you're looking just at the execution block. The only thing that changed in the execution layer block initially was that the mix, one of the administrative fields used to do the proof of work, was replaced with a field from the consensus layers blocks that tells some random number that other contracts were using difficulty to generate random numbers with. And like I said, if you need to be instrumented to figure out if a merge happened, this is how they figure it out. They look at the difficulty opcode, which became the pre-round out opcode, and they see how big it is. If it's really big, you're merged, and you can figure it out. But this makes it clear that the consensus layer and the execution layer split into 2 parts. And in essence, through organic evolution, it accidentally became a modular blockchain. So let's talk about how this happened. So this is a representation of kind of what the inside, oh wow, that did not come well in the PDF transition, whoops. So it looked a lot better on my slides when I submitted it. But here's a brief rendering of what Ethereum looks like on a consensus client. And this is proof of work. So in proof of work, you had on the bottom you had the dev P2P, where all the clients would talk back and forth to each other and would provide all of their transactions to each other, and they'd feed the memory pool and the blocks would be shared. And the top layer represents the JSON RPC interface that web applications would talk with. And I put miners on there too. You can do your mining through JSON RPC. Typically they use something called Stratum, but for simplicity we'll say they're using JSON RPC. And this entire system and the communication channels is how Ethereum worked before you bring in any questions about proof of stake. The first step when they did the beacon chain, all they had for the proof of work was, all they had for the proof of stake was just one connection into the execution layer client to say, hey, who has staked and who hasn't staked and how much do they have and what position they are. So all it was doing was it was reading from the blockchain as it was executing. But at this point we get an important distinction. We have one piece of software that we call the execution layer and one piece of software called the consensus layer. There are 4 different clients that can run the execution layer, and there are 5 different clients that can run the consensus layer. So in essence, there's 20 different combinations of software you can put together to participate, to produce blocks, and participate in the consensus of Ethereum. But this is just the beginning of it. This was just the consensus layer starting to figure out how it can run its own consensus and its stake. The next step came in the merge, where we actually took block production, moved it from the execution layer, and moved it into the consensus layer. So the duties of block production to figure out when a node has to produce a block is now decided by the consensus layer, although the actual building of the block still runs in the execution layer. And you see I've got it connected there in the JSON RPC. It's actually using something called the engine API, which is the same style of communications that all of the clients use, all the distributed applications use to communicate with the client. Different channels, they've got a lot of different security on it, but ultimately on the wire it looks the same. You'll notice that miners disappeared from this. Miners are no longer part of producing the proof of stake blockchain in Ethereum anymore. All the duties that the miners did are now subsumed by the consensus layer. So we've got 2 fully functional modules. Now from this, there might be some other modules that might come out. There's something called proposer-builder separation, where the production of the blocks might even leave from the execution layer and become yet a separate service that is provided by various people, or the execution layer could continue to provide those services. And there's all sorts of other modules that might organically evolve out of it. One other change coming up in this next fork is something called blobs. Blobs are transient data that only stick around on the blockchain for about a month that you don't have to keep forever. And what's interesting is blobs are being stored by the consensus layer, although if you were to look at how they would transition through the system, they would start on the execution layer in the P2P side, and they'd be attached to a transaction. They come up in the mempool, and then they'd be put in a block, and you bring the blob over to the consensus layer, and then the execution layer forgets about it. And then when a consensus layer syncs with another consensus client, it would share it via libp2p. So these blobs are going to be basically everywhere on this map. But for the most part, the consensus layer is responsible for managing these. So what are some key differentiators about Ethereum's proof of stake that you might see from other consensus systems? I think the biggest thing that you need to point out is that this proof of stake is run by multiple clients. There's not one piece of software that runs a consensus. There are 4 execution layer clients and 5 clients. So notionally, there's 20 different ways that you can participate in consensus in the block with all those combinations. There's no proof of stake delegation. If you have stake and you have a key tied to that stake, you cannot have anyone else sign that stake for you. So all of these people who have staked Ethereum, they have machines that have their key active, that they are acting on it. No one acts on their behalf. And I think what also is very important is just the sheer volume of participants we have in this proof of stake network. There are over 500,000 validators. I think that number's gone up since the merge. People have taken some of their earnings and staked in more, and there's more validators coming in. There's over 500,000 independent keys that every 6 seconds needs to do something on the network to participate and keep their stake live and active every 6 minutes. Now these 500,000 validators are split up across right now, I think 11,000 different consensus, 11,000 different consensus nodes. Not 11 million, we're not that big yet, that'd be crazy. But there's 11,000 different consensus nodes. So nodes can handle multiple different validators at the same time to perform the duties for multiples, but they have to have the keys for each and every single one of those validators. This produces a weakly connected topology. You can't connect 11,000 different nodes to each other, so you only connect to some of them and you share the messages. And I think what that really puts in place is that the signature is more important than the network. In some consensus systems, the network connection is what's paramount. The network connection is secondary, the signature of the message is primary. And they also use BLS aggregated signatures, which not all systems do. It's becoming more and more popular. It's a very succinct way to get all of your signatures. When you have to get 500,000 signatures across 32 blocks, you're not putting them all in the block at the same time. You have to aggregate them. So that's where Ethereum is at. Where is Ethereum going? I've identified 3 things that are going to probably represent the next 3 major upgrades to Ethereum that are going to be some of the headliners for these things coming forward. The first one is data scaling. We had a call this morning, all core devs execution, and we're committed to bringing data scaling to the next Cancun hard fork, which is going to ship. I have no idea. We'll figure it out. But it's the next one. And the next 2 ones after that, the only thing we're really sure about is what the next fork is. These are just guesses, and I'm probably wrong on these, or I might be right. But just take it with a grain of salt. When I say the next 2 big features coming in some order are probably going to be something called the EVM Object Format and vertical trees. So what is EIP 4844? What are shared blobs? What is this blobfish thing people are talking about? It's had a lot of names. Blob space, dank sharding, proto-dank sharding, proto-dank scaling, dank scaling. But I think the name that we should probably settle on came up by Ansgar sometime last week, where he wants to call it data availability scaling. We're not actually sharding any of the data. We're not splitting up against some subset of the clients. We're scaling the amount of data that can be used in a transaction without having to commit it to the blockchain. It's a very important thing that's coming on here because of the growth of layer 2s, there's a lot more need for just data in the blockchain. Not necessarily execution time, just raw data. So we need to scale that data, and EIP 4844 is how we're going to scale that data. So like I mentioned on the slides a bit earlier about the layout of the network layout I had of the last slide of the modularity. The duties for 4844 are being split across multiple clients. The execution layer has one set of tasks, and the consensus layer is going to have a separate set of tasks. The execution layer is responsible for finding the transactions that want to use these blobs. So it comes with a new transaction type that you're going to attach the blob to it. Now this transaction is not actually going to go on the blockchain with the blob. It's going to say that it references a blob, but it's going to be gossip between the networks with the blob, if you kind of understand. So in building the blocks, you have to have the data, but in committing it to the chain and committing the chain data, you don't have to have the data. That's where the transient part of the data availability comes in. Now to make these useful, there's a couple of opcodes. There's an opcode being introduced and a precompile being introduced to say what are the hashes that I have attached to my transaction. If you don't have any, it's going to return nothing. If you have 2 or 3, it's going to tell you what those are and what positions those are. And there's another precompile that from that, you can say, okay, so given this blob with this hash, I have this bit of data at this position in the hash. You're not going to bring all 128 kilobytes into the EVM at once. There's simply stated not enough gas. But that's an opcode that's going to help you say that this blob that I brought across, at this point, this transaction, these 256 bytes are at this point of this transaction. We can cryptographically prove it. And that's where the sampling comes from. We only make a sample necessarily available to the transactions when they need it. The consensus layer has a different set of priorities. They're responsible for the month that we need to keep the blobs around for keeping all the blobs in place. At least that's the first pass that they're planning on. They might be able to move to data sampling, where only some of the clients have it, and they can prove that everyone can get it. That might come in the future, and that honestly can be moved over without having to change the way things happen on the execution client. That's the beauty of this modularity. You delegate the duties, and they can do whatever they want. And like I said, these blobs are going to be stored about a month. A month is a magic number. And when you bring a new client up with a consensus, it's going to necessarily have to share these blobs with another consensus layer client that comes up, much like the existing syncing mechanisms that go on. Now to manage these blobs, I mentioned the engine API that was used to produce blogs. The blobs will also be managed via the engine APIs of these blocks. So why go through this big, complicated process of making data available? The reason is for the impact on the layer 2 protocols. Ethereum is committed to using layer 2 technology to get its scaling solution and its sharding solution. that is now the main sharding solution for Ethereum right now. Blobs will allow us to increase our throughput 22 times. What we used to have is a maximum of 90 kilobytes per block that we could put in per block. Sharding allows us to have 2 megabytes per block and allows for a lot of availability of data for a lot more layer 2 networks. I went to L2B and I got all the networks that were live, that were layer 2, or potentially going to be live as a result of this. And these are just some of the clients today that are going to be used. You're going to find this useful. You know, Arbitrum, Optimism, ZK Sync, a lot of the other ZK networks. Some of these are technically Validiums, but even those could have value in using some of these the layer 2 technologies. Now, the reason for the 1 month magic number has to do with interactive fraud proofs that are part of optimistic rollups. Each person has, when you post a block, you have 1 week to challenge it and 1 week to defend it. And so round it up to a full month to deal with delays and everything and trying to figure out if it's going to be valid or not. So ultimately, we need about a month of time for the data to be available for these challenges to happen. Now, layer 2 technologies are not the only use for it. Who knows what the world's going to invent? Maybe some decentralized social networks will start using this. Maybe people will start putting NFTs directly in blobs. We don't know what it's going to be. It's going to be great, whatever happens. The next feature coming up is the EVM Object Format. This is moving into a bit more technical aspect of some of the inside baseball of Ethereum. And what this is a container format for EVM code. Right now in the EVM, there is no container. It's just a random string of bytes. As long as you don't start with EF00, you could put literally any piece of code you want in the EVM and expect it to execute reliably. EVM Object Format changes those rules, and it's going to go a little bit of Marie Kondo on this formatting and say that this goes here and that goes here. And from that, some really nice things are going to evolve. But there are 2 main reasons why we need to do this that are preventing the EVM from evolving. The first one has to do with multi-byte codes. Here's a representation of existing Ethereum code. You've got a couple of push operations represented by 61. And 5B is the jump test operation, which has very special meaning in Ethereum legacy. That's where when you do a jump, that's where your code has to land on the next opcode. It must be a 5B. But there's another rule, is that this 5B cannot be part of an immediate data for a push operation or any other operation. So what happens when we try and add a new, let's say we want 5C to have 2 immediate bytes? The problem is that we change the nature of what the code looks like at that point. Just by changing the EVM semantics, what used to be a valid jump point now is no longer a valid jump point. We cannot safely migrate to new opcodes that take immediate arguments. Everything has to be on the stack. And this is a very constraining, very difficult thing to deal with when it comes to evolving the EVM. The next problem comes with where code lives and where data lives. Putting data in contracts has been a time-honored practice of Ethereum, and even some NFT projects are making it a point to put their NFT data in contracts. But the problem is, unless you're using a specific version of Solidity or Viper, it's hard to tell where the code stops and the data starts. There are some patterns used by some compilers, but these are not enforced by the EVM. This is a particularly well-behaved section of code created by Solidity. It's got 3 different sections of code. It's got a separator. There's no extra data. And Solidity is nice and puts some metadata about what I used to compile it and what the version was. The problem is there's no way to figure out where the code starts and where it ends if you don't use Solidity. If you use a different compiler that doesn't follow these conventions, it becomes unreliable, and we can't bring the Solidity conventions into the EVM without doing a dramatic change. So that's part of the reason for the EVM object format. It was we're bringing these changes into the EVM data structure to make sure that we can do these. Starts out with a container layout. We have a header, and then we have sections of code, and then we have data that comes after that. There's a lot more details that go into that, but that's the big part, is that data goes in data, code goes elsewhere. And you can only execute code that is in the code section. We also require all the code that is in the code section to be actual functional EVM code, which includes things like there's no dead code. If you have bytecode in there, there's got to be some way that it could possibly be executed, and all the operations that you execute must be actual EVM operations at the time the code was deployed. And you also can't jump into the data section. You can only ever execute code. And we validate all those rules with the opcodes through some deploy time validation rules. This allows us to introduce new opcodes that solve a lot of problems that people like zero knowledge networks have. We get rid of dynamic jumps that are based off of data on the stack, and we do relative jumps where the jump destination is a fixed feature of the code. We can also get larger dupe and swap operations. We can add subroutines. The EVM doesn't have subroutines, and to anybody who's been doing virtual machines, that's like 1970s technology. And finally, you can access data in the data section and bring it into your memory and manipulate it. We also introduced stack validation, which gets the compiler people really excited and allows for some really fancy stuff going on. There's also some forward-looking features that we're looking into bringing into the EVM object format. It's not all fixed. This is floating in the air, but these are the operations that I think we're going to actually wind up shipping. The first thing we need to do is we need to get rid of code observability. There's many good reasons why we want to do this, mostly having to do with things like ZK EVMs. We also want to get rid of gas observabilities. If we didn't have gas observability, then the whole Constantinople Petersburg fork issue never would have happened. If we make you send all of your gas to the next operation, the solution to any gas schedule change that breaks your contract is always and forever send more gas, and that will fix it. And finally, we're changing the way we're doing create operations. If we don't have code observability and we can't copy new bytecode into memory, we need new mechanisms to deploy new smart contracts. And we're talking about two different ways. One that takes the bytecode from the container, subcontainers, like thinking a swap pool from Uniswap, and one that can take the new code from a transaction data. And also, every single create can add new data at the end of these contracts. Very important for NFT projects, very important for modern versions of Solidity. So these are, notional of what we want to put in, no commitments. But if we get there, I believe this is going to take the EVM to a wonderful place to make it the nexus of smart contract compatibility. You can take the EUF code and you can change it into legacy EVM. You can change it into future versions of the EVM if we need to change it. You could compile it into WASM reliably and repeatably. And you could also compile it into ZK proof systems. It's a lot friendlier, these things. We're getting rid of a lot of the things that cause problems in it. Now, I don't have time to go into vertical trees. I knew this when I practiced the slides, because the math is just too crazy and too awesome. A big long tree like this is composed of big squares like this, and in essence, we're going to take them into these tiny rectangles. So the takeaway of vertical trees is that your proofs are going to be smaller for really exciting, fancy math reasons. And here we tree them up. So this brings us to Ethereum's endgame. These three features, including the one that I just completely blazed through in 30 seconds, are not all the things we're looking to put in Ethereum. There is a big master plan. If you look at Ethereum, if you look at Vitalik's tweets, twice a year, he'll probably post a new updated version of this quasi-Gantt chart of what's going on with Ethereum. And there's a plan, and we're reaching it, and I think it's going to be an awesome place in the end. I'd like to thank you. If you have any questions, you want to talk about vertical trees, I'll probably be in the developer, the Protocol Village Lounge after this talk.